In this lesson, we'll examine an effect called the common ion effect, and we'll also look at what buffers are, what they consist of, and how we can calculate the pH of a buffer given information about it. First of all, let's look at what the common ion effect is. The common ion effect is the shift of an equilibrium caused by the addition of a compound having an ion in compound with the dissolved substance. So what we're dealing with here is an equilibrium that's been established, and we're going to add a common ion, or one that's in the equilibrium, to that system, and it will cause a shift on the equilibrium. This is a special case of Le Chatelier's principle. So if we look at the weak acid, HF, and we have it dissolved in water, we know that from the hydrolysis reaction that HF in water produces H3O plus and F minus due to the proton transfer. So if we have a system where we've got HF dissolved, at equilibrium we will have some H3O plus and some F minus. Now if that system also contains the ionic solid NaF, or sodium fluoride, it's going to affect this equilibrium. Because if it's just the acid dissolved in the water, then the amount of F minus that we would have would be 0 initially. But in this case, the fluorine from the sodium fluoride is a common ion, and it's going to affect the equilibrium. So let's review just on the side here. What's important when we're dealing with salts being added to systems is that we automatically recognize that they should be broken up into their ions, and this is a complete reaction. It's also important for us to always recognize what our spectator ions are. So in this case, sodium ions are spectators. They're not involved in the equilibrium. They won't affect the equilibrium in any way. The F minus, however, that's produced when we dissolve sodium fluoride in water is our common ion because it is part of the equilibrium. So if we were to examine an ice chart here, we'd have some amount of HF. Okay, the water doesn't matter. Still initially we've got no H3O plus, but we've added a common ion, okay, or F minus. So this side is still going to increase. Okay, this will be X at equilibrium, and the HF will decrease as we move towards equilibrium. So what we can see if we think about this a little bit is that this equilibrium isn't going to go as far forward had there been no common ion. So what the common ion does is it causes the reaction not to go as far forward as it normally would. And we'll see some examples in a few minutes. The biggest difference here is that the common ion, or in this case, the F minus, does not have 0 as its initial concentration because it was provided by the salt NaF. So let's look at this example here. We've got a microbiologist dealing with a system. In this system, we've got 0.1 molar sodium acetate, and we've got acetic acid of 0.09 mole per liter. So the system that we're actually studying here is the acetic acid. It's asking us for the pH, so that's our indication that the system we're studying is the acetic acid in water. So we can write its reaction. Okay, the Ka value for this acid is 1.8 times 10 to the negative 5. Now the sodium acetate here, when it dissociates, will produce sodium plus and acetate ion in a 1-to-1 ratio. So what that means is that the concentration of acetate initially is 0.11. The concentration of the vinegar or of the acetic acid is 0.090. Initially, we've got no H3O+. So when we set this up, we know that the right-hand side is going to increase. The H3O+ has nowhere else to go, so it must increase. At equilibrium, the acetate is 0.11 plus X, and the acetic acid is 0.09 minus X. Now, because this has a small Ka value of the order of 10 to the minus 5, we can make the assumption here. And remember, we're making the assumption that X is so small that it has very little effect on the initial concentrations. So here, this is going to be approximately 0.9, and this is going to be approximately 0.11. When we sub into our Ka expression, we get 1.8 times 10 to the negative 5 is equal to 0.11 times X over 0.09. We find that X is equal to 1.47 times 10 to the negative 5, and in turn, the pH calculated by the negative log of X is 4.83. If you need to pause the video and make sure that you know the calculation, that would be a good idea at this point. Now we can also have a common ion effect with weak bases. So if we examine the equilibrium of ammonia and water, okay, this is the equilibrium we're studying. So in this case, a common ion effect would occur if we added some of solid ammonium chloride. If we added solid ammonium chloride, that would put into the solution ammonium ions, which would depress the equilibrium or not allow it to go as far forward. Nh4+ in that case is the common ion. The common ion effect also applies to our discussion of polyprotic acids. A polyprotic acid is one that has more than one proton available for donation. Now the key here is to understand that with a polyprotic acid, the protons are still donated one at a time. So in this case here, you're looking at H2CO3 losing one proton to form HCO3 plus H3O+. So this is the first equilibrium reaction. H2CO3 is our carbonic acid. So this reaction is going to have its own Ka value. And we would call it Ka1, so that shows that it's associated with the loss of the first proton. Now if we look at the loss of the second reaction, we're starting with the HCO3 minus, and if we put that in water, it's going to produce CO3 2 minus and H3O plus. Okay, and we'll have its own equilibrium constant, Ka2. Now, what we need to recognize is that these reactions will happen in steps. So if I've got a sample of H2CO3, all of the H2CO3 will lose one proton to form HCO3 minus, and then the hydrogen carbonate ions will subsequently react with water to produce carbonate ions. What we have to keep in mind is that the first reaction, the substances that are left at equilibrium, are going to affect the second reaction. So if I've got A amount and B amount of these two ions at equilibrium from the first one, those are going to be my initial values for the second equilibrium. And what this means is that we've got a common ion of H3O plus for the second equilibrium. So the loss of the second proton is greatly inhibited by the presence of the H3O plus. Now, a buffered solution is one that resists the change in pH when we add either hydroxide ions or protons. In biology, you have probably studied already about the buffered solution in our blood. It's really important that our blood keeps a constant pH, and therefore we've got a buffer in our blood of the bicarbonate ion, which will resist a change in pH. This is really important because the pH of our blood, if it changes too much, there are conditions, alkalosis and acidosis, that can occur. For us, what we're going to look at is what are the components of the buffer. We're going to look at how buffers resist pH, how to calculate the pH of a buffer, how to decide what components should be required for a buffer, and actually how to prepare them. So we've got lots of things that we're going to do with the buffer solutions. And these are really an application of the common ion you'll see in the calculations that we do shortly. Now there are two components of a buffer. We need two solutes, and the key is that they need to be a conjugate acid-base pair. And they need to be a pair where the acid is able to behave as an acid and the base is able to behave as a base. So they are prepared with weak acids and bases. So commonly here, if we've got a weak acid HA, a buffer can be made with it and its conjugate A minus. Or if we've got our base B, we can use BH plus as the conjugate pair, and therefore this can be used as a buffer. The previous two examples that you looked at, the CH3COOH with the sodium acetate, that is an example of a buffer combination, as well ammonia and ammonium ions can behave as a buffer. Let's look at first, without calculations, the reason why a buffer can actually resist a change in pH. A little bit later on, we are going to do some formal calculations with this, but for now, we'll just start with a little preview. So if you've got a buffer, it consists of a conjugate acid-base pair. So if I were to make a buffer of HA, I would have in the solution HA and A minus present. The reason that this system is able to resist changes in pH is because if I add H plus or OH minus, it will get consumed. So if I add additional H plus ions, the base in the pair, the A minus, will be able to react to produce HA. If I add hydroxide ions to the solution, the acid in the pair, in this case the HA, will be able to consume those hydroxide ions and put A minus and H2O into the solution. Okay, so let's look at some examples. First of all, eventually we're going to be doing 3 different kinds of calculations. Today, in this lesson, we're going to look at how we can calculate the pH of a buffered system. In the next lesson, we're going to look at the other 2 examples of calculations where we look at the effect of the pH by adding strong acid or strong base. And we're also going to figure out how to decide which acid and salt would work best, and also how to prepare those buffers. First of all, though, we must recognize whether or not a particular pair of substances will be able to act as a buffer. What we're looking for is a conjugate acid-base pair. In this first example with KCl and HCl, we've got a salt here. This salt doesn't affect the pH at all, so it really can't act as an acid or base. And we've got HCl, which is a strong acid. So as soon as you've got a strong acid and a salt that doesn't affect the pH, you're not going to be able to use that as a buffer. In this example here, we've got H2SO4 and HSO4 minus. Okay, so the K here is a spectator ion. So we do have a conjugate acid-base pair, but this is much too strong in order to be effective in preparing a buffer. So the first thing to look for is whether or not you've got one of your strong acids or bases. If you've got one of those present, automatically it's not going to be effective as a buffer. This next example, we've got sodium hydrogen phosphate and sodium dihydrogen phosphate. So let's look at what these salts put into solution. Okay, the sodium hydrogen phosphate puts the ion HPO4 minus into the solution. Okay, and the sodium dihydrogen phosphate puts the dihydrogen phosphate ion into the solution. Sodium, recognizing it's one of the elements from our list of strong bases, is our spectator here. So it won't participate or affect the pH. So what I've got here are a pair of ions, and they are an acid-base pair. They differ by one proton. So because of this, they will be able to be used to prepare a buffer. This is actually the system that's used in the Kodak film process. Sorry. Okay, so looking at this next example here, we've got KNO2 and HNO2. Removing the spectator of potassium, which is from our list of strong bases, we've got NO2 minus and HNO2. HNO2 is not a strong acid. It's one of our weak ones. So this is a good pair. We've got a weak acid and we've got a conjugate salt. So this can be used to prepare a buffer. And what you're going to see in the calculations is that it is the acid here that will dominate our calculations. And so the pH of this particular buffer is going to be less than 7. In this next example here, we've got NH3 and ammonium nitrate. Okay, so ammonia is a weak base. NO3 here is our spectator. And so we've got NH4 plus. Okay, we've got NH4 plus and NO3 minus. Sorry, NH3. Okay, the NO3 minus is a spectator. So we've got a conjugate acid-base pair. So we've got a weak acid and the salt of its conjugate. And that is what we need for a buffer. So this buffer, it's always based on the acid, not on the salt of the conjugate. So this one is based on the base NH3. So what you'll see is that the pH of this buffer will be greater than 7. Okay, so what we have here, if we look at a general solution, so this is on, in your notes, you've got HA plus H2O in equilibrium with A minus. And H3O plus. The calculations that we use in order to calculate the pH of a solution when we're dealing with a buffer are exactly the same as when we're dealing with a common ion. So if I'm dealing with a buffer that consists of HA and the salt of its conjugate, A minus, I'm going to have an initial concentration of my acid, an initial concentration of my base, and no H3O plus present initially. The changes minus X plus X plus X. Okay. And the equilibrium concentration of HA is going to be the same as the initial concentration. The equilibrium concentration of A minus is equal to the initial concentration of A minus. This is because when we're working with buffers, we're dealing with weak acids and bases. Their Ka's are very small, so we're able to make the assumptions. So this is a very important point here, that the concentration of HA at equilibrium is equal to the concentration initially, and we're just going to call this, therefore, the concentration of the acid, okay, which is really this A here. A minus, we're going to call that the concentration of the conjugate base. So when we look at this here, if we want to solve for x, we need to sub into the equilibrium law. And the equilibrium law is Ka is equal to H3O plus times A minus divided by HA. If we rearrange this to solve for the concentration of H3O plus, we get this expression here where it's equal to the Ka times HA over A minus. So the concentration of H3O is equal to the Ka times the concentration of the acid, whatever it is initially, over the concentration of the conjugate base. Now this, because we are always going to be able to make the assumption, this is going to lead us to the derivation of an equation called the Henderson-Hasselbalch equation. The Henderson-Hasselbalch equation you will use to calculate the pH of a buffer solution. The way that it's derived is by looking at the previous expression for the concentration of H3O plus, which is equal to Ka times the concentration of the acid divided by the concentration of the conjugate base. And we're going to take the negative log of both sides. So we're left with the negative log of H3O plus is equal to the negative log, okay, of this entire expression, Ka times the concentration of acid over the concentration of the conjugate base. Using log rules, okay, when we multiply two things, they get added. So we've got the negative log of Ka plus the negative log of the concentration of the acid divided by the concentration of the conjugate base. Now, to make the formula neater, okay, we change this sign to a plus, okay, and what that does is it switches these around, so the conjugate base is the numerator and the conjugate, or the acid, is the denominator. Negative log of Ka is actually just the same as the pKa. Negative log of H3O plus is just the pH. So this is the Henderson-Hasselbalch equation. And you'll be able to use this if you recognize that you've got a buffer. You're going to be able to use it to calculate the pH rather quickly. I remember it by saying pH is equal to pKa plus log of Ba, so to remind me that it's the base over the acid. Now you can always use this equation if you want. You never actually have to use this equation, and I'll tend to use the pH formula, but it is okay for you to recognize that we can do a similar equation for the pOH. Okay? So if we're dealing with a base buffer, okay, you can calculate the pOH directly. I tend to, even when I'm working with a base buffer, I tend to still work with the pH formula and just use 14 minus the pH to find the pOH if necessary. Now it's really important that you understand this formula and how it works, because it's going to be useful when we start looking at how to decide what we're using for a buffer, because this part of the formula is going to be really key. It's also going to be really useful for deciding what ratio we should use to prepare a particular buffer. Okay, so let's look at an example, and this is exactly the example that you did earlier on in the notes with the biologist creating a buffer solution of acetic acid and sodium acetate. In the previous example, I would suggest you pause and go back to it so you can see it. We set up an ice chart, and we used the ice chart in order to calculate the pH. And we found that the pH was equal to 4.83. If you read the problem and recognize right away that you've got a buffer, you can use the Henderson-Hasselbalch equation, pKa plus log of the concentration of the base over the concentration of the acid in the pair in order to calculate the pH. So in this case, you're going to take the negative log of 1.8 times 10 to the negative 5, which is the Ka for the acetic acid, plus the log of 0.11 over 0.09. And you get 4.83, which is the same as before. I'd really encourage you to pause the video and make sure that you know how to use your calculator to do this example. I find it easiest to calculate the ratio first, take the log of the ratio, and then subtract the pKa, or the negative log of the Ka. Now let's compare the pH of this buffered solution to the pH of a pure acetic acid solution that is of the same concentration. So in the last example, the concentration of the acetic acid that we were using was 0.09 mole per liter. So this is the kind of calculation that you did a couple of classes ago, okay, where you've just got a weak acid and you're calculating the pH of it. Okay, so it's really x squared over the initial concentration is equal to the Ka, which in this case is 1.8 times 10 to the negative 5. Okay, in this case, you find that x is equal to 0.00127 and the pH is equal to 2.90. So in an unbuffered solution, the pH is much lower. Okay, so that shows you that the common ion, the acetate ion, does inhibit the formation of H3O+, which makes the pH of a buffered solution higher than the pH of an unbuffered solution. Okay, and really it's closer to 7. Okay, so let's calculate the pH of a buffered solution made from 0.015 sodium acetate and 0.015 acetic acid. Okay, I've got a buffer, so I can use the Henderson-Hasselbalch equation, which is pKa plus log of concentration of B over concentration of A. Now this example I'm showing you because it's a scenario where the concentration of the base and the acid in the buffer are the same. Log of 1 is 0. So at this point, the pH is actually equal to the pKa. And this is an important fact to know because this would be the kind of question you'd be asked in the multiple choice in the AP exam when you don't have a calculator. So even though it might look like you would need to do a calculation, if it's just asking you for the pH and it gives you the pKa of the particular acid, then no calculation is required. It's also important to notice because that took 10 seconds to do that calculation, whereas if you spent the time to set up an ice chart to solve this question, it would take you a lot longer. Okay, so it's an example of where you can be very efficient. Okay, so that's the end of our discussion of buffers, calculating the pH of solutions with a common ion, and some basics about buffers and how to calculate their pH.